In this lecture, we are going to take a look at a real-life application of quantum mechanics, in particular of perturbation theory that we have been studying so far. This is an application of perturbation theory to the fine structure of the spectrum of hydrogenic atoms. Note that I am saying hydrogenic rather than hydrogen, basically because this theory will work for all single electron atoms, that is, not only to the hydrogen atom, but also to systems like helium plus or lithium double plus, etc. ions. Now, we have already studied the quantum theory of such systems in some detail earlier. In fact, we had also done a recapitulation of that in the preliminary lectures in this series. And the Hamiltonian for such systems is given by what we are calling H0 now. And H0 is p square by twice m, or minus h cross square by twice m times the Laplacian. In addition to that, you have the central potential, which is minus z square by 4 pi epsilon 0 r. The familiar Kepler problem, which is exactly solvable. Now, the true hydrogen system is described not exactly by this, but by an additional correction term added to it. This additional term is what I am calling H prime. And as we will see, it is actually easier for the analysis if we split H prime into three distinct terms, which we are naming rather trivially H1 prime, H2 prime, and H3 prime. So where exactly do these extra perturbation terms come from? To understand that, let me just take you back a bit in history, before the time of quantum mechanics. You must remember from your high school studies, or at least from first year in college, that before there was quantum theory, there was quantum theory. That is, you had old quantum theory, in particular the theory of Bohr. Now, the Bohr atomic model was perfectly good in the sense that it could actually explain the spectrum of the hydrogen atom rather perfectly. It predicted quantized energy levels for the hydrogen atom, and using those quantized energy levels and the concept of quantum jumps between those levels, Bohr was able to explain successfully the spectral structure of hydrogen and helium plus, lithium double plus, and so on. In fact, there was a small deviation between what was expected from Bohr's theory and what was observed, say, in helium or hydrogen. And this was explained away perfectly well by the fact that none of these systems really had an infinitely massive nucleus. So you really had to treat them as two-body systems. So the m that you see in the H0 here, that is this mass, had to be actually replaced by reduced mass. And because the reduced mass depended on the mass of the nucleus, hydrogen spectrum and helium spectrum had subtle differences. Using that, you could actually even determine a precise ratio between the masses of the helium nucleus and the hydrogen nucleus. And since you could verify this by other methods, this turned out to be one of the great successes of Bohr's theory. However, even in Bohr's time, optical measurements, the kind of measurements that you did to determine spectra, were really precise. And if you pushed the precision a bit, you could find that what actually looked like single lines in the hydrogen spectrum were not really single lines. You had many very closely spaced lines there. Single lines actually had fine structure. And Bohr's model, dealing with circular orbits, could not explain these additional fine structural lines. Sommerfeld took it upon himself to explain away the fine structure, and the first thing he did was to move away from the circular orbits of Bohr to elliptical orbits as well. Because you could have different shapes for the elliptical orbits consistent with what were now called Bohr-Sommerfeld quantization principle, he expected that you would get slightly different energies for different elliptic shapes, and that would be able to explain away the fine structure. Well, to his dismay, he found out that if you just use Bohr's theory, or Bohr-Sommerfeld theory, to elliptical orbits in hydrogen, you actually found no shift in energy whatsoever. The energy turned out to depend only on the principal quantum number n, and did not depend on the shape of the orbits at all. It was then that Sommerfeld turned to relativistic ideas and tried to incorporate relativity into his theory. And because of the fact that in an elliptic orbit an electron moves at different speeds in different parts of the orbit, hence relativistic effects would have different values in different parts, Sommerfeld was able to actually explain away small shifts in energy and hence land up with an explanation for the fine structure which fitted really well. Now all this was in old quantum theory. When Schrödinger wrote down his quantum mechanical equation, the wave equation, and applied it to the hydrogen atom, he actually recovered Bohr's result exactly. And it was easy to understand why. Because both Bohr and Bohr-Sommerfeld essentially gave you the same result as long as you were dealing with non-relativistic physics, which Schrödinger's equation, at least the version that we know and use, actually talks about. So strictly speaking, these correction terms that we have, the only real way of finding them is by incorporating relativistic effects, that is, move away from Schrödinger's equation and go in for a relativistic theory for the electron. Dirac gave us a perfectly good relativistic theory of the electron, and we will discuss this later on in the course. It is in fact Dirac's equation which in the non-relativistic limit gives rise to essentially Schrödinger's equation with the Hamiltonian H0 plus these correction terms. So strictly speaking, the only way of exactly deriving H1 prime, H2 prime and H3 prime, these terms, is via the Dirac equation. However, the reason why we have split this into three pieces, actually, instead of treating H prime as a whole, is that at least for the first two pieces, H1 prime and H2 prime, you can give heuristic explanations as to where these terms come from, even without going into the full extent of Dirac's theory. Let us now take a look at the three terms that I have been referring to. The first term is called the relativistic correction to the kinetic energy. And it turns out to be equal to minus p to the power 4 by 8 m cubed c square. A term which depends primarily on the momentum and obviously comes from the kinetic energy term. The second correction term, H2 prime, is called the spin orbit interaction term. This basically arises due to the fact that the electron behaves like a tiny magnetic moment because of a spin, angular momentum. And when this tiny magnetic moment goes around the nucleus, it feels an effective magnetic field because from its frame, the proton is going around it, hence creating a tiny current loop. So by taking into account these features, basic electromagnetism, you end up with this particular formula. 1 by twice m square c square times 1 by r dv dr, where v is the standard Coulomb potential, times an L dot s. Now this is the only term where the spin angular momentum makes an appearance. All other terms in the Hamiltonian, both in H0 and H prime, are independent of the spin. But this will play a very important role. The final term is called the Darwin term, and this is one term which cannot really be explained away without taking into account some deeper relativistic theory. Now you might of course say that H1 prime is also a relativistic correction. Indeed it is. In fact, all three terms are relativistic corrections. But let me point out that the first term can be sort of derived without even going too much into relativistic quantum mechanics. Just relativity is enough for that. The second term is also a relativistic quantum mechanical correction term, but can be sort of understood in terms of a magnetic moment going around charged nucleus. The third term, on the other hand, cannot be understood without combining both relativity and quantum mechanics, which is why the third term is somewhat special. And as we will see in the course of the calculation, for a hydrogen atom, H1 prime, H2 prime and H3 prime, all three terms lead to energy shifts which are of similar order. And that is precisely why you cannot ignore any one of these terms with respect to the other. When we talk about spectra of alkali atoms, for example, especially when we talk about the effect of magnetic field on alkali atoms, it will turn out that the spin-orbit interaction term is actually much more important there than the other two terms. But for the current lecture, all three terms are equally important, and we will have to calculate the effects of each one of the three terms. Before we go on to study the effect of the perturbation terms one by one on this unperturbed Hamiltonian, let me briefly remind you about this particular unperturbed Hamiltonian and its energy eigenfunctions and eigenvalues. This, of course, is none other than the Kepler problem. The only difference here is that when we studied the Kepler problem, we had not talked about spin at all. And there's a very good reason for that. The unperturbed Hamiltonian did not have any spin-dependent term at all. The only reason why we are talking about spin here is that one of the perturbation terms, the spin-orbit interaction term, actually depends on the spin, and that is why the spin state becomes important. But as far as H0 is concerned, spin is more or less a spectator variable. Be that as it may, the eigenfunctions of H0 would be labeled by not only the energy eigenvalue, which is denoted by this quantum number n, it will also be labeled by additional quantum numbers L, ML, S and MS, which indicate eigenvalues for the operators L square, LZ, S square and SZ respectively. These are of course operators which commute with H0. This set of operators form a complete set in the sense that once you specify the eigenvalues for each and every one of these operators, a state is completely labeled. You may have noticed that although I said that there are 5 operators involved in this complete set, there are only 4 labels, and the reason for that is obvious. The eigenvalue for S square is always small s into small s plus 1 h cross square, and small s is always equal to half for a single electron system. Since this particular label is the same for all the states, it is omitted from the labeling scheme usually, and that is why you have L, ML, MS as the additional labels beyond n, which denotes the energy. You do not write down small s simply because it does not serve to further specify the wave function involved. Now these wave functions psi, NL, ML, MS depend on the configuration of the electron. I have denoted the configuration here by Q. The configuration contains in it both the position of the electron and its spin state. And because the Hamiltonian H0 does not depend on the spin, it is easy to see that you can split up the wave function into 2 pieces, one depending only on r vector, x, y, z coordinates of the electron, and the other depending only on the spin state. So the part which depends on r vector is written psi n l ml r and is multiplied by the spin state chi, which is dependent on 2 quantities s and ms. S is of course always half, as I've said, and ms tells you whether you are going to get the spin up state for ms equal to plus half or the spin down state for ms equal to minus half. Now if I had typed out this particular set of slides, I would have perhaps used a different typeface for the 2 wave functions psi sitting on the 2 sides of this equation. But because I cannot really do that, and any attempt to do such a thing while trying to write it out by hand is sort of foolhardy, I will not do that. I will just leave you to judge which particular wave function we mean, and there should be no confusion really. When we mean the position space wave function, we just use 3 labels n, l and ml. There is no ms label there. And of course the argument is r vector. So that should be a dead giveaway. The important point is it is only the position space wave function on which H0 acts. So H0 acting on psi nl ml is really En times psi nl ml. The spin wave function chi just comes in for the ride as far as the unperturbed Hamiltonian is concerned. Now we know what the energy eigenvalues are. In fact, we know precisely what form psi nl ml takes. We had already worked that out before. Now the energy eigenvalues take a form which should be pretty familiar to all of you. It depends on 1 by n square, and the precise expression is Ze square by 4 pi epsilon 0 whole square times m by h cross square divided by 2n square with a minus sign in front. The minus sign of course tells you that the energy of the electron in the nth level is actually less than its energy when it's infinitely far away. And that of course proves that the electron is bound to the nucleus. Let me point out that the m here is precisely correct only if we were talking about a system with an infinitely massive nucleus. In a real hydrogenic system, this m would actually be replaced by mu, the reduced mass of the electron. There are several different ways in which you can rewrite this expression for En, and one of them, which is pretty useful, is the one written in green here. Here you see that apart from the z square by 2n square factor, the rest is minus e square by 4 pi epsilon 0 a0, where a0 is the first Bohr radius. And the important point to note here is that this quantity, minus e square by 4 pi epsilon 0 times a0, is actually the potential energy of the electron in the first Bohr orbit, if you think about this classically. From here, using a bit of the virial theorem, it's pretty easy to see why you get an extra factor of half in the total energy. So I will leave you to worry about how that follows. The final version of the expression written in red here is actually quite interesting in its own right, because it sort of shows how the binding energy of the electron in a hydrogen atom compares with the rest energy of the electron. It sort of gives an idea about how important, if at all, are relativistic effects here. Note that this result has no relativity in it so far. This is a purely non-relativistic answer. However, what it does tell you is that the ratio between the binding energy of the electron in the nth level and the rest energy of the electron, En's magnitude divided by mc square, is, apart from a factor of z square by 2n square, alpha square. Now this alpha, which is E by 4 pi epsilon 0 h cross c, is a dimensionless quantity that you can make out of the electronic charge, Planck's constant, and the speed of light. And this dimensionless constant has a very, very important role to play in what is going to come. So important, in fact, that its formal official name is the fine structure constant, because it first came into light when Sommerfeld tried to talk about the fine structure of the hydrogen atom. The value of alpha is also quite interesting. It is pretty close to the reciprocal of an integer, 1 over 137. This shows, of course, that it is quite small. In fact, why is it so close to the reciprocal of an integer gave rise to quite a lot of speculation among scientists in the past, and people like Eddington, for example, spent a lot of their life trying to prove why it is really the reciprocal of an integer, and did all kinds of mystic calculations with it. It so turns out that it really is not 1 over 137. It's slightly, very, very slightly different from that. So those bits of mysticism really did not come to much. However, what is very important is that alpha actually gives you an idea about how strong electromagnetic coupling is, basically because it expresses the charge of the electron in terms of other fundamental constants. And the fact that alpha is pretty small gives you the reason why you can treat electromagnetism perturbatively. And this is why quantum electrodynamics, something that we will study later perhaps, the relativistic quantum field theory of electromagnetic interactions, actually can be handled via perturbative methods. But coming back to the expression for En, notice that what this is telling us is that the binding energy of the electron is actually of the order of alpha square compared to the rest energy. So it's pretty small. So a non-relativistic approximation is a decent place to start. It also tells you that for large values of z and small values of n, the relativistic effects may become substantial because the binding energy for z of the order of say 50 or so is actually quite close to the rest energy. What is of great importance for us in this particular lecture is that this level En is strongly degenerate. Notice that the energy depends only on the label n. It does not depend on the values of L, ML, S, MS. So all the possible values that L, ML, S and MS can take for a given value of n, all of these give us distinct wave functions, all with the same energy, and that is where you get this degeneracy from. Now the degeneracy calculation is very standard, and you have all done this before, that a given energy level En has a 2n square fold degeneracy. There are actually n square distinct values of L and ML possible for a given n. The 2 comes in because MS can be either plus half or minus half. S of course always takes only one value, plus half, and does not contribute anything extra to the degeneracy. This goes to show that for every n, you have a rather highly degenerate set of energy levels. Before talking about the fine structure of the hydrogen spectrum in the rest of this lecture, let me just remind you briefly about the general structure of the spectrum itself. Remember, the energy of the levels depends only on the principal quantum number as far as the Kepler problem is concerned. And if you go by that, when the transition occurs from, say, a level with quantum number NB to another level with quantum number Na, the energy difference becomes the energy of the photon. You divide that by Planck's constant h to get the frequency of the emitted photon. Divide that further by c to get the wave number of the emitted photon. And that tells us that the wave number, nu bar AB, is given by this formula, the familiar Reedberg formula, R bar into 1 by Na square minus 1 by Nb square, where R bar is the Reedberg constant. And the Reedberg constant has a value which can be easily calculated in terms of the fundamental constants. R bar infinity is 109737 per centimeter. This is assuming that the nucleus is infinitely massive. In actual fact, you get a slightly smaller value because instead of the mass of the electron, you have to use a reduced mass, which is slightly smaller. And for hydrogen, the Reedberg constant comes out to be 109679 per centimeter. So you can talk of energy difference between levels expressed in electron volts or some other suitable units. You can also talk about that in terms of the wave numbers. Now you must have seen term level diagrams which look like this, which essentially expresses the energy difference between the 1s level, the lowest energy level of the hydrogen atom, to higher energy levels. There's a big gap here simply because without this gap, the scale would have been too difficult to show. The axis here is actually the energy difference or the wave number in centimeter inverse, 80,000 centimeter inverse here and so on, and the various levels are shown. Now, in the Kepler problem, 2s, 2p, 3s, 3p, 3d, all of these are degenerate. 2s and 2p are degenerate, 3s, 3p, 3d are degenerate, and so on. Now, in this diagram, what we have is not only have we shown the energy levels. I'm going to scroll up a bit so that you can see the rest of the levels. Of course, once you go to high enough quantum numbers, the energy levels get too close together to really show up as distinct lines. So we have only labeled up to n equal to 5, and the lines that have been drawn, the transverse lines here, are lines which indicate transitions. Now, this is something which I have to add here, which is the fact that there is a selection rule. And the selection rule tells us that transitions will occur only between levels where small l, the orbital angular momentum quantum number, differs by plus or minus 1. As a result, there is no transition between, say, 1s and 2s, because that would have led to delta L equals 0. The origin of these selection rules come from time-dependent perturbation theory, something which we are going to study later on in the course. For the time being, let's just accept this as a given fact. The transition occurs only when delta L equals plus minus 1. And so some of these transitions are indicated by these transverse lines. All transitions cannot be shown here simply because that would have cluttered up the diagram a bit too much. In fact, this diagram is something I've copied from Bransden and Joachim's textbook. but this is available in many places in the net. It's a standard document. And these numbers that are written here, 1216 for example, is actually the wavelength of the transition that occurs when a hydrogen atom transits from 2p to 1s level. Notice that the energy gap between these two levels is a bit more than 80,000 centimeter inverse. 80,000 centimeter inverse would have meant a wavelength of 1250 angstroms. The energy gap is slightly more, and hence the wavelength is slightly shorter. Now, all wavelengths have not been shown here simply because that would have again cluttered up the diagram. But as you can see, for example, from the 2p, you can have transition to 3s and 3d, but not to 3p. You can also have transitions to 4s, 4d, and so on. But you cannot have a transition from 2p to 4f, say. But the important point is the transitions from 3s and 3d to 2p, while they're two different lines, actually look like the same line because they correspond to the same energy difference. At least this is before you take the fine structure into account. The whole idea behind the fine structure calculation would be to show that although Kepler problem would have told us that 3s, 3p, 3d have the same energy, they actually have slightly different energies. And because of this slight difference, the 3s to 2p line and the 3d to 2p line, just for example, will have slightly different wavelengths. So if you use an instrument with high enough resolving power, you should be able to see two distinct lines in place of one. And that is the kind of thing that you see in fine structure. And that is what we are going to explain in the rest of the lecture. Let us now turn to calculating the first order corrections due to the perturbation terms one by one. We will first look at the relativistic correction to the kinetic energy, H1 prime, which remember was equal to minus 1/8 p to the 4 by m cube c square. Now, as I have already said, the proper way to derive this correction term would be to start from the Dirac equation of an electron in an electromagnetic field and then go in for a non-relativistic approximation. The zeroth order non-relativistic approximation will give back the Kepler problem, and the first order correction to that will give us this H prime, which we have split into three pieces. The reason that the split was done was that we can understand some of the pieces, in particular H1 prime and H2 prime, in terms of more elementary physics. So, let us try to at least heuristically understand the origin of this particular H1 prime term now. Let us go back to classical mechanics. When I say classical, I mean non-quantum mechanics, and take a look at the expression for the kinetic energy in terms of the momentum. Remember, in relativity, we have this formula E square equals P square C square plus M square C to the 4. The square root of that, of course, is the total energy. If you take away the rest energy from there, what you get is the kinetic energy. And this can be easily rewritten in this particular form. Now, when the speed of a particle is low, that essentially means that P is much smaller than the quantity mc. So this P square by M square C square factor here is a quantity which is small compared to 1. And that means we can actually expand the square root in the bracket here using binomial theorem. And if we do that, here I've just written down the first few terms. What we get is an expression which looks like this. The 1 cancels out with the minus 1 which came from the rest energy, and that of course is what you expect. This is the kinetic energy after all. If there is no momentum, kinetic energy should vanish. And that is exactly what is happening. In fact, if you take the second term, half p square by m square c square, and multiply that by the mc square which is sitting outside the bracket, you are going to get back the term p square by twice m, which is the non-relativistic expression for the connection between the kinetic energy and the momentum. And this is exactly the calculation that we do to show that the classical result or non-relativistic result can be obtained as a limit from the relativistic result. However, what we are focusing on at this stage is the next term. This is the second term or the third term depending on how you count it in the binomial expansion, minus 1/8 p to the 4 by m to the 4 c to the 4. And when you multiply that by mc square sitting outside, you get this term minus 1/8 p to the 4 by m cubed c square. So classically, the kinetic energy term would have been p square by twice m in the non-relativistic limit. In addition to that, you would have an extra piece. And when you quantize the theory, this extra piece is exactly what becomes our first correction term or first perturbation term, H1 prime. Let us now turn to the quantum theory, where we are going to calculate the first order energy correction due to the presence of this perturbation term, H1 prime. Now let me remind you that our unperturbed system is strongly degenerate for a given small n. The energy En is definite, but there are two n squared different independent wave functions, each of which correspond to the same energy En. So strictly speaking, we should be using degenerate perturbation theory here. What that means is we should first form the matrix 2n square by 2n square dimensional matrix by taking the matrix elements of the perturbation H1 prime between the degenerate basis wave functions. Now, as I've already said in the previous lecture, life will be a lot easier for us if we could choose a basis in which the Hamiltonian or this perturbing Hamiltonian is already diagonal. And that is pretty easy to do here, simply because H1 prime, this particular Hamiltonian, involves an operator p to the 4, which is a scalar operator, an operator which does not change when you rotate the coordinate system. And that means that it actually commutes with all components of angular momentum Lx, Ly, Lz. Remember, Lx, Ly, Lz causes rotations in spatial coordinates, and since P is in the same space, P square will commute with Lx, Ly, Lz. It actually commutes with Sx, Sy, Sz by default. So in particular, our Hamiltonian or our perturbation Hamiltonian commutes with L square, S square, Lz and Sz. And so, if you label your eigenstates using the eigenvalues of these operators, that is, if you use L, S, Ml and Ms as additional labels beyond n to characterize your wave functions, to essentially make your choice of basis, then H1 prime is already diagonal in this basis. Just to point out, any two different wave functions in this basis will differ in either L or Ml or Ms, so that means it will differ in at least one eigenvalue of an operator which commutes with H1 prime. And from here it's very easy to argue that H1 prime will have a zero matrix element between different psi n, L, Ml, Ms's, unless the labels n, L, Ml and Ms are exactly the same on both sides. That is, unless you're actually calculating the diagonal element of this matrix. Thus, for this particular choice of basis, H1 prime is already diagonal. And so you can calculate delta E1 by just directly calculating the expectation value of H1 prime in psi n, L, Ml, Ms. You do not have to go through the entire diagonalization process. Please note that this is not an accident. The choice of basis automatically ensures that the matrix is going to be diagonal simply because of the fact that the Hamiltonian, or rather the perturbing Hamiltonian, commutes with the operators whose eigenvalues label the different wave functions here. Rather than evaluate this particular expectation value from scratch, what we will do is notice that this quantity sitting here, minus p to the 4 by 8 m cube c square, is actually directly connected to the kinetic energy operator. By the way, I'm calling this T0 rather than T because this T0 is the classical, or rather non-relativistic, kinetic energy operator, p square by twice m. It's pretty easy to see that apart from a factor of minus 1 by 2 mc square, our perturbing Hamiltonian is actually T0 square. So what we really need is the expectation value of T0 square in the state psi n L ml. Now, in order to evaluate this, what we will do is rewrite T0, which is of course p square by twice m, as H0 minus the potential energy term, and since the potential energy is minus z square by 4 pi epsilon 0 r, T0 works out to be H0 plus z square by 4 pi epsilon 0 r. And when you put that back in our expression, what we get is delta E1 is simply given by this expression. Now, since H0 is a very special operator here, all the wave functions involved are actually Eigen Functions of H0. The calculation simplifies rather a lot. When you open out this square, you get H0 square plus the square of this operator plus H0 times this operator plus this operator times H0. And when you take the matrix elements, or in this case the expectation value, between psi n L in the state psi n L ml, you are immediately going to get En square from the H0 square. You are going to get twice En z square by 4 pi epsilon 0 times the 1 by r expectation value in the state psi n L ml. These two terms come from the AB plus BA kind of term in A plus B whole square. And the square term, B square term, gives you Z square by 4 pi epsilon 0 whole square times 1 by R square, evaluated in the state psi n L ml. Now, in order to proceed further, we will need the values of En, which we have already seen before. We will also need expectation values for 1 by r and 1 by r square in the state psi n L ml. Note that I am not mentioning ms here at all because these expectation values have nothing to do with the spin wave function. It depends only on the spatial part of the wave function. The expectation value of 1 by r turns out to be z over a0 n square, and this actually should ring a bell because in Bohr's theory, the radius of the nth Bohr orbit, which of course was circular, was given by this expression n square by z times a0. It turns out that the expectation value of 1 by r in a fully quantum mechanical calculation is nothing but the reciprocal of the nth Bohr radius. Evaluation of the 1 by r square expectation value takes a bit more work, and I'm just quoting the result here. In the assignments, we will see how to derive these expressions precisely. Notice that the 1 by r square expectation value is sort of like the square of the 1 by r expectation value, except that instead of an n to the 4 in the denominator, you have an n cube times L plus half. Now what we need to do is take these three quantities En, 1 by r expectation value and 1 by r square expectation value, plug them back in this expression for delta E1, and then after some algebraic simplifications, you will end up with this expression for delta E1. The first order correction in the energy level En due to the first term H1 prime in the perturbation. Note that delta E1 actually depends on N and L. This means that the degeneracy that was there in the Kepler problem, that all levels with the same N but entirely different values of L, ML and MS had the same energy, is lifted a bit because of the delta E1 term. Now, the energy levels are still degenerate after this correction to changes in ml or ms, but they do depend on the value of L. Now this is consistent with what I said while talking about the Kepler problem. Central force field nature of the potential dictates that the energy will depend on N and perhaps on L, and it is a bit of an accident in a sense that in the Kepler problem the energy does not depend on L. In the actual hydrogen atom, energy does end up depending on other parameters besides N. In particular, this expression depends on L. Now delta E1 is one term in the calculation which tells you how much the energy level in the Kepler problem shifts because of the additional perturbation terms. Notice that the fractional change delta E1 by En is of the order of alpha square. This is the place where the fine structure constant gets its name from. The fine structure of the atomic levels, which translates into fine structure of atomic spectra, is controlled by this parameter alpha square, as you can see here. Let us now turn to the second term in this perturbation scheme, H2 prime. This is the spin-orbit interaction, and I've already given you a semi-classical way of thinking about this as the energy shift which occurs because of the spin magnetic moment of the electron going round the nucleus and hence experiencing a magnetic field caused by the nucleus. The expression we have for H2 prime, 1 by 2 m square c square times 1 by r dv dr times L dot s, can be rewritten in a form which emphasizes the important features here. You can write that as xi of r times L dot s, and this way of writing it sort of emphasizes the importance of the interaction between the orbital angular momentum L and the spin angular momentum s. The prefactor xi of r, of course, is an important part of the calculation, and given the fact that capital V, the Kepler potential, is minus z square by 4 pi epsilon 0 r, you end up with this final form for xi of r, which is 1 by 2 m square c square z square by 4 pi epsilon 0 into 1 by r cube. Before we go on to discuss the calculation of the first order energy correction due to the term H2 prime, let us take some time to settle the question of degeneracy. We started with the Hamiltonian H0, where the energy level En was 2n square fold degenerate because it was degenerate against the variation of L, ml and ms. After we had applied H1 prime, this degeneracy had been lifted somewhat. The energy is now dependent on both N and L, but not on ml and ms. So we still have some degeneracy left over. The important question here is, when we apply H2 prime on this problem, can I treat H2 prime as a further perturbation acting on the same degenerate levels? In other words, does H2 prime respect the degeneracy which is imposed by H1 prime? A very important point to be considered here is that L square commutes with this extra Hamiltonian perturbation term H2 prime. And this immediately leads to the fact that H2 prime does not connect unperturbed eigenstates with different values of L. Now what this means is that the matrix element of H2 prime between our basis eigenstates with different values of L would actually vanish. Now we have been using statements like this several times, especially in this lecture. So let me at least once show you exactly where this comes from. We start with the obvious statement that the commutator of H2 prime with L square is 0, and then we take the matrix element of this particular commutator between two eigenstates, one with eigenvalue small l into small l plus 1 for L square, the other with eigenvalue small l prime into small l prime plus 1. Now this matrix element, being the matrix element of an operator which is 0, has to vanish. Now because the two states involved in the matrix element are both eigenstates of L square, it follows rather readily that this expression becomes L into L plus 1 minus L prime into L prime plus 1 times the matrix element of H2 prime. And this immediately shows that unless L is equal to L prime, this particular matrix element is going to vanish. So although if we treated H2 prime as the perturbation on the unperturbed levels due to H0, a 2n square by 2n square matrix, all terms with different L values will actually vanish. So the problem for H2 prime naturally splits up into matrices where you have non-zero element only between the same small L valued states. And this structure is nicely consistent with the corrections imposed by H1 prime, which has told us that the 2n square levels are no longer degenerate, but there is still degeneracy as long as states with the same value of L are concerned. So the problem of finding out the first order energy correction due to H2 prime splits up into solving a 2 times 2L plus 1 fold degenerate set of problems, one for each of L equals 0, 1, 2 up to n minus 1. The 2L plus 1 fold degeneracy simply comes from the fact that ML can take 2L plus 1 different values for each given L, and the extra factor of 2 of course comes from the 2 possible values of MS. So instead of one 2n square fold degenerate problem, this now splits into n distinct degenerate perturbation theory problems, each with different dimensionalities. Now of this, the L equal to 0 level has degeneracy only due to the 2 possible values of ms equal to plus half and ms equal to minus half. But it's easy to see that for L equal to 0, all the matrix elements of H2 prime vanish simply because L dot S has 0 matrix element when sandwiched between states with L equal to 0. So the non-trivial calculation for the first order correction due to H2 prime has to be done for L not equal to 0. So for a given small l, we need to diagonalize a 2 times 2l plus 1 dimensional square matrix. That's of course better than having to diagonalize a 2n square dimensional matrix, but still quite a lot of work. It would of course help if we had a choice of bases in which the perturbation was already diagonal. Then of course we would have to do no calculation whatsoever other than finding out the diagonal elements themselves to find out the energy correction, at least to first order. And in that case of course the basis functions that you would use would already be the 0th order wave functions from which further calculations could proceed. Now you cannot always rely on luck to get such a basis. It did happen that for H1 prime, the basis that you would naturally start out with, the set of psi, NL, ML, MSS for the same value of n, was already one in which H1 prime was diagonal. That of course followed from the fact that the operator p to the 4 was rotationally symmetric and depended only on spatial coordinates. As a result, it commuted with L square, S square, Lz and Sz. H2 prime on the other hand has this operator L dot S, apart from a part which depends only on small r. Now it is easy to see that L dot S would commute with L square and S square, but it's also pretty easy to figure out that it will not commute with either Lz or Sz. And as a result, the psi, NL, ML, MS, which are simultaneous eigenstates of H0, L square, Lz, S square and Sz, would not really be a basis in which the perturbation term, which involves L dot S, would be diagonal. You could of course use this particular basis to do the full calculation and then diagonalize a non-trivial square matrix. In fact, we will actually illustrate such a method in the next lecture when we talk about fine structure of alkali atoms, for example. However, in general, this is not a great basis to start from because you will have a non-trivial problem to solve. Now, in general, degenerate perturbation theory does involve solving a secular equation, that is, the characteristic equation for a d by d matrix where d is the degree of degeneracy, but it would definitely help to have a nice choice of basis to start from. And it so happens that in this particular problem you can actually find a nice choice of basis. This involves the notion of an alternative complete set of commuting observables. Just like A0, L square, Lz, S square and Sz were a complete set of commuting observables, so that you could label energy eigenfunctions uniquely by using the eigenvalues of each and every one of these, there is another complete set of commuting observables available here, and that happens to be A0, J square, Jz, L square and S square. And this of course gives rise to an alternate choice of basis where the wave functions are actually eigenfunctions of A0, J square, Jz, L square and S square, and this set would typically be denoted by psi n, L, J, Mj. Once again, the eigen label S, not really the eigenvalue but the eigen label, because it labels the eigenvalue for S square, is not mentioned simply because at least for one electron atoms this label is always half. This wave function psi n, L, J, Mj is an eigenfunction of A0 corresponding to eigenvalue En, L square corresponding to eigenvalue L into L plus 1 h cross square, S square corresponding to 3/4 h cross square, half into half plus 1 h cross square, of J square corresponding to eigenvalue J into J plus 1 h cross square, and of Jz corresponding to eigenvalue Mj h cross. Now you have actually seen this eigenfunction in some detail when you talked about addition of angular momentum in an earlier semester. Of course, the basis is not a single wave function psi n, L, J, Mj, but it is the set of all wave functions psi n, L, J, Mj put together. And if you take a look at a specific value of n and L, you end up with a set of eigenfunctions, exactly 2 into 2L plus 1 eigenfunctions corresponding to different values of J and Mj. And this is the basis with which we are going to start, simply because L dot S obviously commutes with J square and Jz simply because it is symmetric under rotation. It of course commutes with L square and S square simply because all components of L and all components of S commute with these operators. So it turns out that if we were to choose this particular set as a basis, then H2 prime will come diagonal already within this basis set. In fact, the expectation value of L dot S, the thing that we need to calculate, can be evaluated very easily in this case, starting from the simple result that L dot S is half of J square minus L square minus S square. Remember, this really should have been L dot S plus S dot L, but L and S commute. Now this form makes it even more obvious that this expression commutes with J square, Jz, L square and S square if you wanted any further confirmation of that. And this is what actually tells us that psi n, L, J, Mj is a good choice of basis for this particular problem. So now that we have a good choice of basis, let us try to calculate the first order energy correction due to the extra piece of the Hamiltonian H2 prime. So this is our delta E2, the second piece in the correction. Now delta E2 will now be something and figure out simply by taking the expectation value of half xi r times J square minus L square minus S square. This of course is H2 prime in the state psi n, L, J, Mj. So what you need to do is take the expectation value of xi r in this state, but the rest of the thing, which depends not on the radial wave function but only on the spin and orbital angular momentum part of the wave function, is easy to evaluate since each of these, since the state here is an eigenstate of J square, L square and S square, is pretty easy to figure out that this quantity J square minus L square minus S square will simply translate to H cross square times J into J plus 1 minus L into L plus 1 minus 3/4. And this, apart from the calculation of xi r's expectation value, This is actually what delta E2 is going to be. Now, as I have mentioned already, for the Kepler potential, the psi r is given by 1 by 2 m square c square z is square by 4 pi epsilon 0 times 1 over r cube. So what we need to do is calculate the exponential value of psi r, and that involves the calculation of the exponential value of 1 by r cube in a state which is labeled by n and l. Note once again that this is a purely radial calculation and this involves just the eigenlabels n and l. Now this exponential value of 1 by r cube can be calculated using standard methods. This once again will be an assignment, and it turns out to be z cube by a0 cube. This much should be sort of obvious from the pattern that we have seen before. NL dependence is slightly more complicated. It turns out to be n cube times L into L plus half into L plus 1. Note that for L equal to 0 this would have diverged, but we have already seen that the L equal to 0 case has no spin orbit splitting, so we can safely ignore that. Now putting all of these together and using the fact that J can take two distinct values L plus half and L minus half, it takes a small bit of algebra to calculate delta E2 and put it in this particular form that you can see on your screen right now. For L equal to 0, of course, delta E2 is 0. For L not equal to 0, delta E2 works out to be minus En times Z alpha whole square by twice n into L plus half into L plus 1. Now, this has to be multiplied by either L, which means the L in the denominator would have cancelled, if J takes the value L plus half, or by minus L plus 1, if J takes the value L minus half. So for the two cases, J equal to L plus half and J equal to L minus half, you have these two alternate expressions for delta E2. Final piece of the perturbation, H3 prime, the Darwin term, is what we are going to consider next. Now in the Darwin term, you have this delta of R vector, and that is the only quantity here which is not just some constant. As a result, this particular term in the perturbation is diagonal in L, ML and MS, and it also vanishes unless L equals 0. Now this last piece is because the delta of R vector can only pick out contributions from a wave function at R equal to 0, and only L equal to 0 wave functions can have a non-zero value at R equal to 0. This, remember, follows from the centrifugal potential barrier term, which forces the wave function to vanish at the origin whenever L is not equal to 0. Now once again, because this perturbation is already diagonal in L, ML and MS, you can directly calculate its value, especially for just L equal to 0. For all other cases, this will vanish anyway, and you get delta E3 given by pi h cross square by twice m square c square times z square by 4 pi epsilon 0 times psi n00 delta R vector psi n00, this particular expectation value. Remember, we really have n, L, ML here, but only L equal to 0 case will give you a non-zero value, and for L equal to 0 the only possible ML is 0. So this ultimately is nothing but psi n00 at the origins modulo square. Now you can easily calculate this using standard properties of the wave function or the Kepler wave function, and it turns out that the value is minus En into Z alpha whole square divided by n. So we now have completed the calculation of delta E1, delta E2 and delta E3. Time has now come to put them all together. Let me point out that I did not carry out the details of the calculation here. You will have to fill in the blanks in between. Once you add delta E1, delta E2 and delta E3 together to get the total energy shift due to the fine structure perturbation terms, you find that the final result is a bit surprising. The energy shift delta E, as you can see, has two labels, n and j. This means that the energy shift depends on the value of n. That was of course obvious. But what is perhaps not so obvious is that it depends only on one other quantum number, which is small j, the total angular momentum quantum number, not on small l, despite the fact that the individual terms that we calculated did depend on small l. So this is a rather surprising final result, and once again you will have to fill in all the steps to be able to convince yourself that this is really correct. But let me point out some features of this expression. This factor that you see in the square bracket at the end, n by j plus half minus 3 by 4, this is a factor of the order of 1. It's actually typically near about 1, sometimes smaller, sometimes bigger, depending on the value of n and j. But also note that the largest possible value which j can have is actually n minus half. That's because the largest possible value of j is the largest possible value of l, namely n minus 1 plus a half, and that is why j can only go all the way up to n plus half. What that means is that the n by j plus half factor in front is always bounded by 1. It cannot go below 1, and therefore the square bracket is actually a positive number. Z alpha whole square by n square obviously is positive, so delta Enj has the same sign as En. Let me remind you that En is negative because this is a bound state. So the effect of fine structure perturbation terms is to actually lower the energy consistently. All the energies get lowered because of that. Also, since the factor in the square bracket is of the order of 1, basically the fine structure splitting in the energy level is controlled by the Z alpha whole square by n square factor. So compared to the actual energy of the level, which remember is already proportional to 1 by n square, the fine structure splitting has this extra factor of 1 by n square. So higher levels split less. There's also an important factor of alpha square, which says that the fine structure splitting is really at a fine or very small level. Alpha, remember, is 1 by 137. So alpha square is of the order of 10 to the minus 4, actually a bit less. So apart from the fact that there's a 1 by n square factor, it's the alpha square which really dictates the overall size of the fine structure splitting, and as a result, as we have been saying, this constant alpha deserves the name fine structure constant. The expression that you see in blue is actually the total energy of the level with quantum numbers n and j. It's of course what you get when you add to delta Enj the original energy En. Now the reason why I have written this is that this allows you to compare the result that we have obtained through perturbation theory to first order with the exact result which comes from the Dirac equation treatment of the hydrogen atom. And the Dirac equation expression is a bit more complicated, as you can see. But if you were to actually calculate this to the lowest order in alpha, you will find that it does give you back exactly the expression for Enj that we had obtained above. So the fact that the energy depends only on n and j and not on L is a feature also of Dirac's exact solution. This result that we have got from first order perturbation theory actually persists to all orders. At the end of the day, the important result is that while we started with a 2n square fold degenerate level, En, we now have a lower degree of degeneracy. This degeneracy has been partially lifted. Of course, states with the same n and j still have the same energy, but since the given n can correspond to several different values of j going from all the way from j equal to half to j equal to n minus half, there are distinct energy levels available now. So this is where the fine structure splitting of energy levels and hence the fine structure splitting of spectra come from. We are now going to take a look at these issues in more detail. Let me remind you once again that the fine structure splitting delta E and J, at least to first order, is always negative, as you can see from the expression, and the splitting of course increases with larger values of this bracket n by j plus half minus 3/4. That is, the smallest value of j causes the largest shift. Now for n equals 1, there is only one possible value of L, and that is 0. And so small j can take only one possible value, which is half. So while the n equal to 1 level is shifted because of the fine structure correction, it is not split. There is only one level even after incorporating the fine structure correction. But for other levels, when n is more than 1, you have several levels, and the splitting of course depends on the energy difference between the two extreme parts. And an idea about how big the splitting is can be obtained by looking at the energy difference between the two levels which have been shifted, which have been split by the largest amount, that is the one which has been shifted the most, that is the one for the smallest value of j, and the one which has been shifted the least, the one for the largest value of j. That means we have to look at the energy difference or the difference in this quantity delta E and j between j1 equals n minus half, the largest possible value j can take, and j2 equals half, which is of course the smallest value which j can take. And if you just substitute these two values and subtract, what you will get is this expression for small delta E, and that works out to be mod of En into z alpha whole square by n square into n minus 1. This is the change in the two energies, the difference between the two energies. And this expression can be rewritten in atomic units by realizing that En is given by z square by 2n square in atomic units. And so you see that the largest split that you get actually sort of behaves like 1 by n cube, right? Because there's an n minus 1 in the numerator, but there's an n to the 4 in the denominator. So higher levels are of course split less, and even the largest splitting becomes reduced when you go to higher and higher values of n. Now for the two adjacent levels, that is for j1 equals L plus half and j2 equals L minus half, for a given L you have these two values. Of course you can have these two values only when n is more than 1 and hence L is more than 0. Even for n larger than 1, L equal to 0, you will have no such splitting because there is only one j allowed in that case, that is j equals half. Once again, the result is very easy to calculate, and the result works out to be mod En z alpha whole square by n into L plus 1. And expressed in terms of atomic units, you again get alpha square z to the 4 by 2n cube L into L plus 1. Once again showing that even the splitting between nearest levels also depends essentially on 1 by n cube. The alpha square factor is there in both cases, which determine the overall scale of fine structure splitting. But even within that, higher levels are split less. In order to realize the order of magnitudes that we are talking about, it's important to talk about some numbers. Remember E1, the binding energy of the hydrogen atom, was 109,679 per centimeter. Since alpha is 1 over 137, it is pretty easy to figure out that E1 times alpha square, the quantity which actually sets the scale of the whole thing, is 5.844 per centimeter. Bear this in mind. This is the tiny amount of shift that you would see in wave numbers, and it is actually a great testament to the amount of ingenuity of experimentalists that they can routinely measure such changes nowadays. With this number under our belt, let us now take a look at the fine structure shift in the energy levels in hydrogen for some low energy levels. Let us start from the bottom here. For n equal to 1, as we all know, there is only one possible value of L equals 0, and hence J can only take one possible value of half, and there is only one term in the spectroscopic series here, 1 s half. I hope all of you know that this 1 here stands for the N, the S or the P or the D, or for higher levels F, stand for the L value, and the quantity that you see written out here is the J value. So 1s half means N equals 1, L equals 0, that's the S, and J equals half. Now for 1s half, you can easily calculate the N by J plus half minus 3/4 to simply be 1 by half plus half, that is, this is 1, minus 3/4, so you get 1/4. So that's the factor which determines the overall size. So what you have is that this is going to be 1/4 of the quantity 5.844 centimeter inverse that we just calculated, and you're going to get 1.46 per centimeter. That's the energy shift in wave number units for the lowest state n equal to 1. Let us now take a look at the n equal to 2 level. Let me remind you that the original level, the unperturbed one, had a degree of degeneracy d of 2n square, which turns out to be 8. Now what about the situation after the perturbation is taken into account? There are two distinct values of j possible, j equals half and j equals 3/2, and that means you are going to get a splitting of the levels, not only a shift but also a splitting. The original unperturbed level is going to split into two levels. These levels are still degenerate. Note, the 2p 3/2 level up here has 4-fold degeneracy, simply because for j equals 3/2 you can have 4 distinct values for mj, minus 3/2, minus half, and plus 3/2. 2s half still 2-fold degenerate, and 2p half, again mj can take only 2 values, minus half and plus half, so 2-fold degenerate. So the original 8-fold degenerate unperturbed level has split into two very close levels which have 4-fold degeneracy each. As far as the sizes of these shifts are concerned, note that n by j plus half minus 3/4 for these values of n and j are easily seen to be 1/4 for the j equals 3/2 case and 5/4 for the j equals half case. So the relative size of the splittings is going to be controlled by that. As you can see, this shift is going to be 5 times bigger than this shift. That means the gap here is going to be 4 times bigger than this gap. That is exactly what is written here. This one is 0.365 per centimeter, as opposed to this one, which is only 0.091 per centimeter. So the factor of 4 is clearly seen. What you have to remember is that there is an overall factor of 1 by n to the 4 between n equals 1 and n equals 2. So the shifting for n equals 2 is already smaller by quite a lot. N equals 3, an even smaller shift. You can easily figure out that the original 18-fold degenerate level has split up into 3 levels, and these 3 levels have their own respective degeneracies, which you can figure out very easily. And it is easy to see from the value of n by j plus half minus 3/4 noted on the right exactly what the splittings are going to be. Okay, let me just warn you that these diagrams are definitely not to scale. In any case, the actual energy gap between the levels is of the order of 100,000 centimeter inverse, whereas the fine structure splitting is of the order of 1 centimeter inverse. So there is no comparison between those two scales. Even within the fine structure splitting, the scale for different n values is chosen quite differently, simply because of the extra 1 by n to the 4. It would be very impractical to show them all to the same scale. Of course, energy levels are not directly measurable. What are measurable or observable are spectral lines. So the question is, how does this fine structure splitting of the energy levels reflect in fine structure of spectral lines? So earlier we had levels which were labeled by n and l values. The energy, of course, depended only on n for the hydrogen atom, but you had transitions from a given nl to a given n prime l prime. The L value is important because of the fact that there were selection rules, delta L equal to plus minus 1. From time dependent perturbation theory, something we have not studied yet. So it's not the N value alone which told us which transitions could take place. It was the L which actually controlled the transition. So that is why when we are talking of the transitions, we are talking of NL to N prime L prime transitions. Now, the selection rule delta L equal to plus minus 1 is still in force now. But now what has happened is that the line which came from NL to N prime L prime transition has now become a multiplet of lines which started from the level with labels N, L and J and ends up at level with labels N prime, L prime and J prime. Just to illustrate this, let me point out once again that the selection rule is delta L equal to plus minus 1, and consistent with this selection rule, you can have delta J equals 0, because even for the same J, you could have L equals J minus half and L equals J plus half, and thus getting a difference of plus 1. Delta J could also be plus or minus 1. So these are the possible values which will allow transitions to occur. Now, just to illustrate this issue for some specific cases, let us consider the situation when you have a transition from an NP, some N value, to N prime S. So L equals 1 to L equals 0. Now, here the NP level splits into 2 because of the fine structure effect. J can take 2 values, half and 3 by 2. So you have 2 levels. For N prime S, there is no splitting. There is a shift, but there is no splitting. So you have only one level, N prime S half. And for both of these levels, transitions are possible because both of these levels, from both of the upper levels to the lower level, you can have transitions. Now, in this case for ND going to N prime P, so a transition from D to P, D of course is L equals 2. So now you can have two different J values, 3 by 2 and 5 by 2. These are larger J values, so the splitting between here is different also because of the larger value of N compared to N prime. In N prime you have N prime P 3 by 2 and N prime P half. There is another shift. So you have another pair of levels. Now because both the upper level and the lower level has split into 2 levels, you would expect 4 lines, but because of the selection rule that delta J can only be 0 or plus minus 1 and not go beyond that, you do not have a transition from the ND 5 by 2 to N prime P half. So you end up with only 3 lines in the multiplet. So these are the multiplets that show up in fine structure. So let us now turn to the question of splitting of specific kinds of series in hydrogen. As you all know, the largest frequencies that you obtain in the hydrogen spectrum occurs when the transition happens to the lowest energy level, N prime equals 1. Now, N prime equals 1, of course, has only L equals 0 possible. So, the only possible value of J is J equals half. No splitting. The lower level is not split at all. And because L is 0 for the lower level, the only possible transitions can occur from L equals 1, that is from P levels. So you have two possible sets of transitions from NP half to 1s half or NP 3 by 2 to 1s half, where N is the principal quantum number for the upper level. For the L alpha line, the first line in the Lyman series, the transition occurs from N equals 2 to N equals 1. So the N equals 2 level splits into 2, one for J equals half, the other for J equals 3 by 2. Now, these are the S levels and here you have the P levels. From the 2s to the 1s, there is no transition possible because delta L equals 0 is not allowed by the selection rules. Although I have kept on saying that you will understand them later on when we talk about time-dependent perturbation theory, there is a sort of easy heuristic way of understanding this. The photon is a spin 1 particle. So the photon which is emitted takes an angular momentum of 1 unit. which is why there has to be an angular momentum change by 1 unit during the transition. So from S to S you cannot have a transition, but you can have a transition from P to S. There are two possible transitions here. 2p3 halves to 1s half is one of them, and 2p half to 1s half is another. As a result, the Lyman alpha line, which looks like one single line, actually splits into two distinct lines if you use a very high resolution spectrometer. L alpha, which looked like one line using a standard spectrometer, is actually two lines. Let us wrap up this lecture with a discussion on one of the most famous set of lines in the hydrogen spectrum. This is the Balmer series, where the transitions occur from some higher level to a lower level with n prime equals 2. The reason why this is the most famous is simply because many of these lines are actually the visible region. So they were the first ones to be discovered. Now, for the lower level, n prime equals 2, you can have s equals 0, L equals 0, or you can have L equals 1. So you can have either S or P. Now, because of the delta L equal to plus minus 1 restriction, you can only have transitions from 2S from P, higher levels, and to P, that is to the 2P level, you can have transitions from higher S or higher D. Let us take a look at the possible lines. When you look at S half, the possible transitions are from NP half and NP3 by 2. For P half, you have transitions from NS half and ND3 by 2. From P3 by 2, you actually have possible transitions from NS half, ND3 by 2 and ND5 by 2. So there are 7 possible kinds of transitions here. The diagram on the right here illustrates the situation for the Balmer alpha line, H alpha. This is the first line in the Balmer series, the one which corresponds to a transition from n equals 3 to n equals 2. Note that this looks like a single line in the spectrum if you are not using a very high resolution spectrometer. What we have just shown is that this should actually split into 7 lines, but let us take a look at this in some more detail. For n equals 2, as I have said already, you can have two different values of L, that is L equals 0 and L equals 1. So you have the S level and the P level. And J can take two distinct values, J equals half, which is possible for both the S orbital and the P orbital, or J equals 3 by 2, which is only possible for P. Now, as we have already said, the fine structure shifting always shifts the energy level down from the unperturbed value, but it shifts the lower J values more, which is why J equals half, the two J equals half values are at the same level here, and they are all both below the J equals 3 by 2 level. The situation with n equals 3 is you have 3 possible values of L corresponding to S, P and D. For S, you can only have J equals half. For P, you can have both half and 3 by 2. And for D, you can have 3 by 2 and 5 by 2. And note once again that even after the lifting of the degeneracy, the levels with the same J value are still degenerate. So 3S half and 3P half are degenerate. 3P 3 by 2 and 3D 3 by 2 are degenerate. 3D 5 by 2 has a higher energy than that. And the energy gap here is also slightly smaller than the energy gap here. Now let us take a look at the possible transitions. Let me remind you once again that the rule is delta L has to be plus or minus 1, which means that to the higher of the two energy levels for n equals 2, which is 2p 3 by 2, transitions are possible only from 3s or 3d. You can't have transitions from 3p. And the smallest energy gap for these transitions is the one which has been labeled by A here. This is a transition from 3s half, the lowest of the n equals 3 energy levels, to 2p 3 by 2, the highest of the n equals 2 energy levels. As you climb up in the frequency spectrum, the next transition is the one which is caused by the next higher energy level in the n equals 3, transiting down to the same 2p 3 by 2. Now this one has to be 3d 3 by 2 because a transition from 3p 3 by 2 to 2p 3 by 2 is not allowed. So this is the line labeled by B here that has a slightly higher frequency than A. The next step in frequency would be the line C, which is from an even higher level 3d 5 by 2 to 2p 3 by 2. Now we have two lines which are both labeled in green in the diagram. One is a transition from 3p 3 by 2 up 3p half here to 2s half, and the other is a transition from 3s half to 2p half. Since the 3s and 3p levels for j equals half are degenerate according to Dirac's theory, and the 2s half and 2p half are degenerate according to Dirac's theory, or according to our first order calculation that we did, we would expect these two lines, though corresponding to different transitions, have exactly the same frequency. And a very similar situation occurs for the two lines labeled in blue. These are transitions which occur from 3p 3 by 2 to 2s half and 3d 3 by 2 to 2p half. The lines labeled F and G should again have exactly the same energy difference and hence the same frequency. So what we expect here is that despite the fact that there are 7 transitions, we should be able to see 5 distinct lines only in the fine structure. And if you use a high resolution spectrometer, that is exactly what you see. So this was a huge vindication of using relativity in quantum mechanics, which allowed us to explain clearly the fact that the single lines in the hydrogen spectrum were not really single lines. They had fine structure. They were really several lines. At this point, let me add one more thing. Now let me tell you that while our theory does say that the lines labeled D and E in this diagram, as well as the lines labeled F and G, should have the same frequencies respectively, and hence only contribute 2 lines to the spectrum instead of 4, it so turns out that in actual very high precision experiments, you can see that they are different lines. Now, this should come as a surprise because not only our first order calculation, but even Dirac's more precise result did tell us that the energy depended only on N and J, so the 2s half and 2p half or the 3s half 3p half levels should have exactly the same energies. It turns out that if you take quantum electrodynamic effects into account, you can explain this further splitting, which is called Lamb splitting or Lamb shift. The name of this shift is after Willis Lamb, who along with Rutherford first did a very high precision measurement where they demonstrated the fact that 2s half and 2p half do have different energies. They did not show that these two pairs of lines have different frequencies. What they did show is that you can actually directly simulate a transition between the 2s half and 2p half energy levels by using microwaves. Remember that energy difference here has to be very, very tiny. Should be 0 according to Dirac theory. The actual shift is not 0, but it's very, very tiny, and the corresponding frequency is very low. So this is in the microwave region. Both the Lamb-Rutherford experiment, which was a high point in experimental precision at that time, and the calculation of this shift theoretically by Hans Bethe and others, are landmarks in the history of physics. They went a long way towards establishing quantum electrodynamics in particular and quantum field theory in general as realistic pictures of the world. In the next lecture, we will take a look at what happens when we switch on an external field like a magnetic field on an atom and what effect does that have on the spectra. Until then, bye.